So vectors can be used to describe a lot of physical phenomena. In fact, if you take any physics course, you're going to be using vectors a lot. They're incredibly useful when you know how to use them. So here we have a 25-pound box is resting on a ramp that has an 8-degree incline. So that looks like it's something like this. We have a box here. This incline is 8 degrees, and we know that this box weighs 25 pounds. Now, we're going to round to the nearest tenth. We're going to find the magnitude of the normal perpendicular component of the force, the force of gravity, that's the weight of it. And we're going to find the component of the force that is parallel to the ramp. So the ramp prevents the box from going down. So when you think about the weight of the box, it's pulling it straight down. That's how weight works. You know, it always pulls to the center of the earth. But effectively, this is reducing how much weight is pulling the box down the ramp. So because the ramp is there, like the box can't go into the ramp. So it's going to be, the ramp is actually pushing against the box. And so less of the box's weight is pulling it down. There is some pulling it down, but not the full weight, not 25 pounds is down the ramp. So what we want to do is find these two things. We know this 25 pounds going down. And this is the perpendicular component because it's going perpendicular to the ramp. And this component here is parallel to the ramp. So these are the two portions that we're trying to find. I'll do it like this. V normal for the normal component. It's called normal for physics reasons. It's actually really pointing this way, but it doesn't really matter. And then we also have, this is going to be the V parallel. So VP and VN, those are the ones that we're trying to find. All right, so when you're looking at this, what we're really trying to do is figure out how do these things compare to this 25-pound vector here. That's the direction it's pointing, and we know its magnitude is 25 pounds. So really, if we can figure out how these angles interact, what we have here is this one, and then straight down is this one. We got to figure out where does this 8 degrees play into these angles. Because then we can use sine and cosine. We can use all those stuff, the trigonometry to help us find the actual lengths, the magnitudes of these things. So that's what we're trying to find, magnitude. If I were to draw this a little bit more accurately, it might give you a hint to where the angle is. Really 8 degrees is a very small degree. So something more like this. It's a very, very, very slight angle on the ramp. So this is the box, and we have the weight of it is going straight down. I'm going to exaggerate the perpendicular vector a little bit so that you can actually see a difference, but it looks something like this. And then this is the parallel vector here. And you can see that as I decrease this angle, which I didn't actually draw it correctly here, but as I drew it more correctly, you can see that this angle here and this angle here also decreased. In fact, that angle is the same as 8 degrees. There's a few ways you can convince yourself of that. I'm going to draw it like this. I'm going to draw the end of the ramp here. This is the end of the ramp. And we can actually think of these things as, this is the 25 pounds down. This is the vector parallel to the ramp. And as I change this angle, it's going to end up changing the perpendicular angle by the same amount. So as I bring this up, this portion is also going to go down. This is still going to stay the same because it's always pointing towards the center of the earth. So whatever angle this goes up, this will go in because they're tied together. They're perpendicular to each other. So that same angle, this angle is actually the same as this angle here. It's going to be the same as this angle here. It's going to be kind of pivoting on this point here. and that's what gives you the 8 degrees. So if this is 8 degrees, this is also going to be 8 degrees. Okay, hopefully that convinces you, and now we can work on the actual mathematics. So what we want to have is we want to have each of these components compared to this. So we know that this here is 8 degrees. The way that the forces work is that we're going to have this triangle here. This is 25 pounds. And this one here, this is the normal force, and this is the parallel force. These are right angles to each other. It's the same as right angles here and here. It's all the same. And this is 8 degrees, which means this one must be 82 degrees. And we can find the vectors, these vectors, by using this magnitude for these ones, because the magnitude of a vector is the same, is going to be found by its components, and we can think of this as a horizontal component or a vertical component, and the other one. So in this case, I would think of them as a horizontal and vertical. So I'm just going to rotate just slightly. 25. This is Vn, and this is Vp. So, of course, my triangle is completely off because the angles aren't at all realistic, but that doesn't matter. What matters is the numbers. We have a horizontal component here, a vertical component, and how do we find those? Well, we just look at the cosine and sine of this angle. So really we have Vn is going to be, well, this is the vertical component. You can use right triangle trig if you want. It's going to be sine of 82. So 25 times sine of 82. That's just rearranging the right triangle trig. And that's going to give us 24.76. This is in pounds. Now the parallel component is going to be the cosine of 82. And that gives us about 3.48 pounds. So what I did here is I rewrote the vectors in a way that was easier to see what mathematics we have to do. And really, if you can create a triangle out of something, that's going to help you out. Both Vn and Vp depend upon the weight of the box. This may not be obvious, but it is true. When you study physics, you're going to notice that the more the box weighs, the larger Vn and Vp are going to be. The smaller, the smaller. So really, this kind of triangle, which you can rotate around to make it a little bit easier to see, doesn't really matter. Once you have a triangle, the right triangle trig is what will get you there. But the hardest thing is probably figuring out what angles go where. And that's where I kind of showed this 8 degrees. As long as you can use that to give you your angle, that will create your triangle for you, and then the right triangle trig will get you to where you're going. Okay, two children are throwing a ball back and forth, and they sit in the back seat of a car. So they're kind of facing each other along the same line. The ball is being thrown 8 miles per hour relative to the car, and the car is traveling 45 miles per hour down the road. So to draw a picture of this, I'm going to just draw a box for a car, and it's going this direction at 45 miles per hour. So 45 miles per hour is the magnitude, and the direction is the forward direction. Now, inside of the car, the children are throwing the ball, left and right. It doesn't really matter which direction they're throwing because we're only looking at one period of time, and it's going 8 miles per hour. So let's just, for the sake of, having a single direction, let's just say it's being thrown this way when a child doesn't grab it. It doesn't really matter, like I said. If it's going the other way, it's be the exact same thing, just a different direction. But it's still effectively the same thing. Now, if the child does not catch the ball, what direction does the ball fly out of the window at? So this is the opening. Is it going to fly this way? Is it going to fly this way? Is it going to go this way? Going to go more that way, lower that way, more an angle. You know, what's the direction that we're looking at here? Well, all that really matters is the vectors on the ball as it leaves the car. Once it's outside of the car and no longer being affected by the car's, the children throwing it or the car's motion. What is it going on? And these are the two vectors that act on the ball. So the ball is like right here. It's moving at a 45 miles per hour because when a child was holding onto it, it was moving 45 miles per hour in the forward direction. But now it's also moving 8 miles per hour this way. But using vector addition, let me write this on the other side here. That's the same thing as moving this way. That means the ball is going to move in this direction. So it's going to move forward and off to, in this case, I moved it off to the eastward direction. Doesn't really matter. Could also be moving to the leftward, to the westward direction. That's just how I chose to do it here. So that's what the direction is. Let's actually find an angle for this. So the angle is going to be this angle here because we're going to kind of think of it as eastward. You could also find it on this angle here, but I think this one's more natural because it's not just going straight out. It's actually going forward more. And this angle is going to be a component of this vector. It's going to be the angle of this vector here. And we know this vector because it's going to have the x coordinate 8 and the y coordinate 45. Nothing's been changed. The 45 is directly vertical and the 8 is directly horizontal. So that means it has the components 8 and 45. So the actual angle that it's moving is going to be y over x. This, of course, is in the first quadrant. That's how I drew it. I mean, that's why I drew it this way. Makes it nice and easy to solve. And doing this in a calculator, I get 79.92 degrees. So that's the angle. It's going to be in a northeastern direction, 79.92 off of the directly eastward direction. So, of course, it might not be eastward if the car's not driving north. You know, whichever way the car is driving, it's going to be pointing mostly in that direction. But that's the idea here. You could, of course, find the magnitude. Let's just find it real quick. The speed the ball is going once it leaves the car is going to be 8 squared plus 45 squared, the square root of that. So it's going to go at a 45.71 miles per hour. Give it a try in numbers 5 and 6.